Okay, welcome to continuous growth and decay. Everything we've talked about before has been, okay, you wait a certain amount of time and then you double. You wait a certain amount of time and you get 5% interest, stuff like that. But this is what's talking about, what if it's always growing? What if I put an investment into an account and I just see the cents constantly ticking up? Well, maybe not so constantly, depending on how much money I put in. If I don't put in a lot of money, the interest rate, even with continuous, is not going to grow very fast because we do round to the nearest cent. Anyway, let's look at a little example, a little exploration here. Okay, we're going to go on an adventure together. So if I, Jason, invest $1, so not the best investment, but watch this, at 100% interest. Now that is a good deal, okay? For one whole year, complete the table below. I'm going to leave a little bit of room before I write this table. Okay. So it'll depend on how frequently it compounds. All right. And I'm curious, how much am I going to have after a single year? So in general, right? A of 1, let's remember our formula, right? A of t is equal to P times 1 plus R over N raised to the N times T. So after 1 year, we have the principal, which is 1. You'll need to write that 1. Times 1 plus R, which is our interest rate, as a decimal. Move it over 2 decimal places, just 1. Over N, which I haven't told you yet, raised to the N times T, which is 1. Okay, so this value is just going to depend on N. All right. So if it's annually, right, N is 1. If N is 1, right, we're going to have 1 plus 1 over 1 raised to the 1. Well, 1 plus, that's 1 plus 1. That's 2 to the first power. That's 2. So if it compounds annually, I'm going to have $2 after the year. Okay. What about if it's semi-annually, right? That's N is equal to 2. We'll get 1 plus 1/2 squared. Okay, N is 2. So you're just replacing in the formula, N is 2. That'll be 3/2 squared. That'll be 9/4. That'll be 2.25. So after a year, if it compounds semi-annually, I'll have an extra quarter. Great. All right, and remember, the more frequently something compounds, the more money we're going to make. But I'll show with this table that it doesn't go on for forever. I can't become a millionaire in a year if it compounds really, really fast. All right, that's impossible. So let's see what does happen. If it doesn't go off to infinity, it must go somewhere. All right, so I'm not going to do this all out, but I want to show you what happens. If it compounds quarterly, we're going to have $2.44. Even more. If it compounds monthly, and it'll be 12, we're going to have $2 and about 71 cents. I'm going to keep on going. 2, 1, that's not a 4. 2, 1, 4, 5, 6, 7. If it compounds daily, 365 or 366 times in a year, how many is it going to be? It's going to be 2.718127. And if it compounds minutely, we have 525,600 minutes. All right, great. And we're going to have $2.71, sort of with some other stuff. So notice that the more frequently it compounds, the bigger the number's getting. But the change here is big, a quarter. A quarter. Change here is smaller, right? That's 19 cents. Change here is about 27 cents. Change here is not even a cent, even less than a cent. Look how similar these are, whether it compounds daily or minutely. These are approaching E, Euler's number. Okay, so that's what Euler's number is. Okay, and again, his name is written like that, but it's pronounced Euler. Euler's number right here. E, which is about 2.71828, etc. Okay, so that's where this number comes from. And it's a number that we write with a variable, just like pi, right? Pi is 3.141592653, etc. I could embarrass you with how many digits of pi I learned in high school. Okay, we write it not as a number, but it is a number. Okay, and that's what it means. It means if something is growing continuously, then this is that growth rate. Okay. What we can do right here is if we're investing money and it's not continuing, if it's not compounded like discretely a certain number of times, right? As n goes to infinity, if it's compounding as we speak, it is growing. As we speak, my pile of cash just climbs to the roof, right? Then that rate is that E. So again, we still are investing P, but the rate, our B value, if you will, is E. All right, and the interest rate will be the same interest rate as before. Okay, so this has to do with exponential growth that's continuous as opposed to discrete. So like the growing size of like, a bacteria culture might be able to be modeled continuously, even though on a very, very small scale, you either have one or you have two, sort of a thing, but like a mass could be thought of with this continuous growth, all right? And in general, we think about a lot of things with this continuous growth, okay? So let's use this and we'll go back to our a, b to the x as well. Example 7 though. Let's go back to Janet. How is Janet's income, or let's not say income, how is Janet's investment changed if it compounds continuously? Am I running out of ink? I feel like I haven't used this pen that much. And you guys go through a lot of math apparently. All right, so let's go back to Janet's situation. I'll invest this pen later. In the meantime, you guys get a red pen running low itself, right? It's a little harder to read red, but it's easier to read red than nothing at all. So remember, right? Janet invested $2,000. The interest rate was 0.0275, I believe. Yeah, it was 2.75%. And we were talking about 10 years. Okay. So if it were compounding continuously, we would have A of 10 is equal to P, which is still 2,000, times E, which is Euler's number, to the R, 0.0275, interest rate is a decimal, times T, which is 10 right here. Let's plug that into a calculator and see what we get. All right. So if we do that, what do we get? We're going to get 2,000 times E raised to the, make sure you have parentheses, you have multiple things going on here, 0.0275 times 10. We're going to have $2,633.06, all right, rounding to the nearest cents. Well, if you remember back from what we had earlier, right, if it compounded quarterly, it's $26.30 and 58 cents. Compounded monthly, it was $26.32 and 23 cents. So compounds continuously, we get an extra 83 cents. All right, an extra 83 cents. Whoa! How exciting! All right, extra 83 cents. I don't think cents actually goes through all the way, but it's something like that. All right, if you want to say $0.83, that's good as well. I also just guessed. I think that's the actual difference. All right. So how has it changed? Not much. Okay. And that's how you sort of do it. That's E. So let's revisit an earlier topic I said, right? We had y is equal to a times b to the x. And if b was bigger than 1, it was growth. And if B was between 0 and 1, it was decay. Well, we can also model these things as A times E to the RT. And again, A is the same thing. But we can standardize it in a sense by, instead of having a bunch of different bases, we can standardize it with E, Euler's number. Okay? And here, if R is positive, that'll be a positive growth rate. All right? And it'll be growth. If R is negative, oops, that'll be decay. All right? That's a big thing to think about for growth and decay. Growth and decay looks different. If it's in this form, b to the x, we have to think, okay, is it bigger than 1 or smaller than 1? If it's in this form with Euler's number E, then we have to look, is it positive or negative? All right, so it can be confusing and easy to get those mixed up. Example 8, and then we'll finish this video. All right, growth or decay. Part A, y is equal to 2 times e to the 0.75t. And you can just plug in some numbers too if you want. You can plug in some different numbers of t and see, is this getting bigger or is this getting smaller? All right, so you never really have to guess. You can always just evaluate it and see what it's going to look like. All right, but right, r here is 0.75, and that's positive. That means it's going to be growth. If I look at something like b, y is equal to 2 times e to the negative 0.75t. Oh, or apparently 0.075t now, right? Our r value is negative. So it's going to be decay. Our c, y is equal to 2e to the 5t. Again, r is 5. It's positive. It's going to be growth. And that's how you do it for continuous growth like this with e. But again, remember that if you do have something like this, we go back to our earlier definition. This is not really a model for continuous growth. It's positive, but it's still decay here. The decay rate is 1/3. Okay. Just watch out, that can be confusing with our two different forms. Okay. One you have to check, is it positive or negative? The other one you have to check, is it bigger or smaller than 1? All right. Good luck. Wait, let me double check. Yep, that's the end. Good luck.